This is Mission Control Houston. We're going to be going down to the NEEMO 16 mission, which is kicked off and is going to be going on for the next 2 weeks. Yesterday we were joined by Stan Love. Today we are lucky to be joined by Mike Gernhardt, who's the principal investigator for NEEMO 16. So Mike, thank you so much for joining us. Let's talk about what's going on today down there off the coast of Florida.
Okay, so what we're trying to do is jump out into the future, 15 years, and understand what it's like at the nuts and bolts level to work on an asteroid. And so we've got three aspects of this mission. One was a robotic precursor that we did months ago to document the remote sensing of the coral reef in the area of the Aquarius habitat. The second element of that is that we're diving with these deep worker submersibles that are highly maneuverable, single-piloted submersibles that are the analog of the space exploration vehicle that we're developing under the AES program. And then the third aspect is the saturation crew, who are saturated in the Aquarius habitat, and they're out investigating different methods of restraint, translation, and different sampling techniques for what it would be like to actually work on an asteroid. And today they're on day 2 of the EVA-only circuit. As we say, we've actually developed an underwater asteroid that's about 500 feet across, and there's all these different sampling sites that we're using consistently with different restraint and translation techniques.
Let's talk about translation a little bit. You know, it sounds like something that would be so easy here on Earth, but anybody who has watched a space station spacewalk knows that, moving around and figuring out where to put your hands and your feet is, one of the biggest challenges of doing a spacewalk. So talk a little bit about how that's different. How is it more challenging on an asteroid, and what are you guys learning in terms of that?
Yeah, great question. And I always say, like, asteroid is like the worst combination of lunar and microgravity. On space station, we have complete control over the translation paths. We have handholds. We have all these different restraints, foot restraints, body restraint tethers, and so forth. On an asteroid, we have none of that. And so we're investigating laying out translation lines that we would anchor at one point, probably fly the SCV across to another point where we could anchor that line. We're trying to understand how much stability we get out of these translation lines and what kinds of tasks we can do on them. The other thing we're looking at is this thing we invented that we call the lightweight boom. And picture this telescopic boom that we anchor at one end, and then you deploy it, and then you can anchor the other end, and then you can short tether yourself to it or use a body restraint tether and then reach down and do the sampling tasks. And then you can release the anchor at one end and sort of step the boom across the asteroid. Of course, we don't know if we really can anchor to asteroids of different characteristics. And so what we're assessing here is the benefit of these different techniques if we could anchor. And then the third thing that we're looking at with the crew today is use of jetpacks. And that looks good for certain tasks, but not for other tasks. Later in the mission, we're going to bring the submersibles up and work with the crew, and they'll actually be in foot restraints on the end of an astronaut positioning arm on these submersibles that are the equivalent of the SEV, and then we'll repeat the same circuit with those techniques, and we're collecting all these metrics to understand what the best combination of restraint and translation systems, crew size and distribution, all those kinds of things that will inform a more optimal and cost-effective development of the hardware when we actually go to an asteroid or a moon of Mars.
So you said the word jetpack, so I have to ask about that. Are we talking about looking at something like what Bruce McCandless used back during that famous shuttle picture? Is it sort of like that or what?
Yeah, so it's quite a bit, will be quite a bit different than the safer jetpacks that we have on space station. We'll have a lot more delta V. It will be sort of a nominal thing versus a contingency thing. We're simulating that underwater with a thruster pack on the back of the crew members, and we're looking at it today as a jetpack only, and that's probably not totally realistic in the sense that if we didn't have a space exploration vehicle, you would have to go from the deep space hab, potentially a kilometer or so away, to the asteroid and back. And if we have to do that with a jetpack, it becomes something more than a jetpack. It becomes a device that you can do targeted burns and so forth. But what's looking promising from NEEMO 15 and the work we've done in our asteroid sim is the combination of this very capable jetpack and the space exploration vehicle where astronauts can be on a positioning arm or they can skirt off the vehicle with this jetpack and do some local reconnaissance, maybe pick up what we call a float sample, which is just a rock that's not attached to anything. And then when we have to do the more detailed, hammer chip samples or deploy seismic devices or drills and so forth, the SEV would then come in and the crew members would get in the astronaut positioning arm and do the more fine task, much the same way we do on station with the SS RMS.
We talked to Stan yesterday about what it's like to work in the water and how closely that mimics what we would see in space. But I want to get your take on it too. What does the water teach us, and how what are sort of the pros and cons of doing it?
Yeah, and there are pros and cons. The good thing about water is we can be neutrally buoyant. We do have the viscosity and the drag of water, which becomes more of a factor the faster you go. So on these very slow, methodical, close-in tasks, it's actually a pretty good simulation. And as we know from the neutral buoyancy lab training that we do, it's about as good a integrated choreography simulated environment as we can get, but it's not the only environment. So we actually have within our analog program another simulation of an asteroid where we've integrated that with the virtual reality lab and the jet packs so that we have the proper dynamics of microgravity. And so we I always say that each analog is one chapter in the story of how we're going to work on an asteroid. And so we have to do all of these different analogs and then put those chapters together to have the story of the path forward to working on an asteroid.
So what is ahead for the crew? I mean, this is early on in the NEEMO 16 mission. So what are they going to be doing for the rest of this week and next week, and what's ahead for them?
So they're doing what we call the EVA-only circuit now, and they're evaluating, again, this standard set of tasks across this 500-foot, simulated asteroid under different techniques. So they'll be doing that through Friday. And then starting Friday, we bring the submersibles up, and we start doing the same circuit with the divers, saturation diver crew members on the submersibles in different combinations of working with just an astronaut positioning arm and one crew member outside. Another condition we call condition 6B is two astronauts on the submersible or space exploration vehicle. One is on the astronaut positioning arm, the other is on a jetpack. And then we have another variation where they can go on and off the arm and jetpacks and so forth. And again, we have very specific metrics by which we evaluate our performance and scientific results. And so then there'll be like 4 days of that. There's also some other life science habitability psychological experiments that we're doing inside the habitat. And of course, I failed to mention that all of this is being done with a 50-second each way time delay. And that's a big difference between anything we've done in space previously and what we're going to have to do on an asteroid. And by simulating that, we really get into the nuts and bolts of the best way to manage the operation, to assimilate the data, to do replans and so forth. And we're learning tons every day from that.
So last question for you, Mike, as somebody who's been in space before, does it get you excited as we get closer and closer? I mean, every time you guys do one of these tests, it puts us that much closer to actually going and flying one of these missions in the future. So how do you feel doing something like that?
Yeah, no, that's a great question, and it really is exciting because I think we're doing this thing right. We're, instead of writing requirements and building hardware for years and years and years, and then figuring out how we're going to operate at the nuts and bolts level, our great team is jumped out ahead, and we're trying to understand those operations early enough that we can inform the design of cost-effective hardware. And I'm very optimistic. I'm actually very pleased with what we're learning. If you go back 2.5 years, no one had the first clue of how humans were going to operate on an asteroid. Now we're talking specific tool designs and operational methods, and it does make it just that much realer. And then I also am optimistic that because of the work we're doing, when we go to develop this hardware, we can do it more cost effectively. And I think we need, as an agency, to learn how to do that because we have, essentially limited funds, and we need to go and do exploration with the funds that we have. And this is part of that whole process.
Well, Mike Gernhardt, we want to thank you for joining us. It's exciting stuff you guys are doing down there. We're going to keep watching how the team is operating over the next several days down there off the coast of Florida. Of course, if you would like to follow along with the NEEMO 16 mission or check out some of the webcams that are currently broadcasting from the bottom of the ocean floor, just log on to www.nasa.gov/NEEMO. Once again, www.nasa.gov/NEEMO.